This is the final video lecture for this week. Sections 1, 3, and 1, 5. Again, you should be reviewed, but let's get through this. So first off, trigonometry, which you need to remember a lot of trig in this class, but in case you've forgotten, the way it works is I plug into these 6 functions down here an angle, and what comes out are certain quotients of the sides of the triangle. So if I use this sin, the sine function, then I get the opposite of this theta divided by the hypotenuse, and so on. These are all basic definitions, and you should know them. Now, the unit circle is the way we usually compute trig functions of special angles that are common. So the way it works is we end up getting this circle of radius 1, and if you drew a perpendicular down to the x-axis, you would end up with a circle, or sorry, a triangle whose angle is t. And this is kind of like this situation where I have a theta instead of a t, but it's theta is Greek t, so it's okay. And so the cosine, since I'm in a circle of radius 1, this hypotenuse is equal to exactly 1, and so when I have this triangle here, the cosine is the x value, and that's because the cosine is the adjacent divided by the hypotenuse, and like I said in the unit circle, the hypotenuse is 1, so I just get the bottom, and so that's why it's this x-coordinate of this point, and the sine will give me the y-coordinate of the point, this vertical length, because the sine is the opposite divided by the hypotenuse, so I get this side divided by 1. And so if I plug in certain angles, I'll get certain things happening. So if I plug in angle 0, I in fact get no triangle whatsoever. You can say this is a triangle with height 0 if you'd like, but the coordinates are 1, 0 at this point, and that tells us that the cosine of the angle that got us there, the angle 0, is 1, and the sine of the angle 0 that got us there is also equal to 0 because it's where the height is. Now, we only use radians in here, never degrees, and there are good reasons for this that I'll explain later. So pi over 2 radians is this 90-degree angle that takes us to this point here on the circle, and this tells us, okay, then that the cosine, the x value of pi over 2 is 0, because the x value of the point right here is 0, and the sine of pi over 2 is 1, because the y value of this point here is 1. And if I plugged in 3 pi over 4, I get this point, and so on. Now, I'll only expect you to be able to work with the standard unit circle, so this picture, and this has all the information you need to compute the trig functions of common angles. So, if you want the cosine of 5 pi over 6, then the cosine is the x-coordinate, and so you can immediately say, because I look at 5 pi over 6, I look at the x-coordinate of this point, and I can say the cosine of 5 pi over 6 is negative root 3 over 2. The sine of 5 pi over 4 is negative root 2 over 2, because the sine gives the y-coordinate, and so on. Now, we use this to solve equations with trig functions. So here's an equation I would like to solve, and we put this restriction here on the theta so that we don't get infinitely many solutions. If you remember your trig, these functions oscillate up and down and are wiggly forever. So if I want to solve this equation, then what I do is first I isolate the trig function, so I get sine by itself, and I now have arrived at the equation sine of theta is minus 1. Now remember, in the unit circle, the sine gives me the y-coordinate of the point. So this equation is basically asking me to find the angles, to find the thetas, the angles, for which, when I take their sine, the point on the unit circle has y value minus 1. That's what this is saying. So we look at this circle, and we look at all the points around the edge here, all the way around, and we try to identify all of them whose y-coordinate is minus 1. You'll find, if you search through carefully, that this is the only one down here that has this property, with the y-coordinate being minus 1. So, to report the answer to our question, we look at this angle, because remember, the variable is theta, so we're looking for a theta, we're looking for an angle. The answer then would be this 3 pi over 2. Okay, here's another example. Cosine of theta divided by 2 equals minus 1/4. Again, I want to isolate the cosine, so I'll multiply by 2 and I'll end up with this equation. And this is saying the cosine of theta is negative 1/2. That is, the x-coordinate of the point on the unit circle must be 1/2 if we're going to say that theta is the answer. So we will go back to the unit circle and we'll say, okay, look through all these points and find the ones whose x-coordinates are minus 1/2. And you'll find one here, and you'll find one here. And again, we want to report the angle back as the solution. So we'll have two solutions. We have 2 pi over 3 and 4 pi over 3. I wrote 7 pi over 6. Why is this? 7 pi. See? 7 pi over 6, I was looking at the sine coordinate. So this is a mistake. So it's actually 4 pi over 3 and 2 pi over 3, because we're interested in cosine theta is minus 1/2. That is the x value of the point's minus 1/2. I apologize for that mistake. So, when you go through trig, you end up getting into all these formulas and things, and this is great. These first ones are pretty elementary, and the second ones, I would only memorize this first one and never memorize these, because you can figure them out, and I can show you this in the future. For these things down here, don't bother memorizing them. If they're relevant, I will give them to you, okay? There's no point in memorizing them. And I have to say this because, yes, I use trig functions all the time, but I don't have them memorized either, so why should I expect you to do this as well? Okay, so that's trig functions, like crash course in them. Exponential functions. Now, exponential just means that the variable is at the top. Now, this is different than the polynomials we were looking at earlier, where the variable was the bottom. So like when we had a polynomial of order 2, this was x power 2, and so the power was a number that did not change. Exponentials are the opposite. Exponentials, the power does change, and that's what makes it exponential. Okay? Now there's a special number e that you hopefully have heard of, but if not, it's about 2.7182, and just like pi, it's an irrational number. In fact, it's an irrational transcendental number, whatever that means, and this means that you're never going to write out its decimal perfectly. So the symbol e is the best way to write this number. Okay? Now, that means that e to the x is going to be the exponential that we use most often. You can have other numbers as a base, like 2 to the x or 3 to the x, but as for reasons we'll see soon, there's a very special property that e to the x has that no other exponential does, and this is why it's such an important function. Now, logarithms are the way we invert exponentials. And by invert, I mean, if I have an equation with an exponential in it and I want to solve for this exponent, what do I do? Because I can't take square roots or anything like this because it's not a polynomial. So what I actually do is I take a logarithm. And so logarithms have the property that if I plug, there's a logarithm for every base. So if I plug the logarithm of base b, if I plug into that the exponential b to the x, it's like these guys are canceling out. Log base b of b to the x gives me x, and b to the log base b of x is x. So the point is that this is some kind of cancellation property, and the logarithm's defined so that this property holds. Now again, like I said, the exponential that we'll deal with pretty much all the time is e to the x, and therefore the logarithm that we'll deal with pretty much all the time is the logarithm with base e. And this is, I write log for this. Some people interpret that to mean base 10, but no mathematician on earth does that. So, when I write log, I'm really meaning ln, or the natural log base e. You could write it this way if you wanted. I will accept this, and it's very common to write ln for this as well, and that's because some people want to make sure there's no ambiguity of does this mean base 10 or base e or whatever. But I will likely interchangeably sort of use both of these in time. Okay, I won't be able to control myself. I'll just start writing, and then halfway through the problem I'll realize, I used log, or I used ln. So just be comfortable with the usage in both ways. Okay. So what are some properties? Logarithms have nice properties. For instance, if you have two things multiplied inside of a logarithm, then it turns into a sum. And this is the property that logarithms were really developed for. They were developed a long time ago to help people deal with large calculations. So, if you have two numbers multiplied, this is maybe harder to calculate than the sum of two numbers. And this can be exploited in things like slide rules. These are old mechanical calculators to make complicated calculations. And then there's this quotient property where if I have the division of a over c inside the logarithm, then it comes out as subtraction. And then this exponent here has the property that it pulls exponents out to the front. This is what logarithms do. So these are properties that we will use all the time. So let's look at an example, okay? Now the properties of exponents are the standard properties of exponents, by the way. So if I have e to the x times e to the x, then what happens is I add the exponents, okay? And you learn this in college algebra when you're multiplying, say, polynomials together. Okay, so let's look at an example of solving a logarithmic or exponential equation. So I have this equation, e to the 2x plus 1 equals 5, and again we can interpret this, graphically, if we wanted to. So, okay, so there's e to the 2x plus 1. Exponentials tend to look like this, where to the left they go very close to 0, and to the right they blow up very fast. And in fact, we'll see later that they're faster than any polynomial. So e to the x grows faster than, if a polynomial of order 10 trillion, eventually, okay? So the high order polynomial may get fast quicker initially, but in time, the exponential always wins. So in this problem, we want to solve this equation. So we also want to see, where does this black curve intersect this red curve at height 5? Now we can get a numerical value right here at 0.305, 5, and this is not what I want. I want an exact solution. Because like I said, there's these irrational numbers and we can't represent them perfectly with decimals. And so this is a nice approximation, but this is not the exact answer. So how do we find the exact answer? Well, okay, like I said, logarithms are the inverse of exponentials. So if I want to get rid of this e, what do? I plug this left side into ln, and I get this expression. Now, if I do something to one side of an equation, I have to do the same thing to the other side. So I must also plug this side into ln, and I get this expression over here. Now, the reason I chose to plug this into ln is so that I get this cancellation. So now that I have an ln next to an e, they annihilate each other like matter and antimatter, and poof, they're gone, and I'm left with the exponent. 2x plus 1 equals ln 5, and now this is reduced to a linear equation like the previous section. So you solve for x, and you have now this perfect answer, ln 5 minus 1 over 2. Now let me humor you and plug this in, if the internet works, and find the decimal value for it. Maybe this doesn't work. Okay, point is, this is how you do it. Now I can solve equations that are ln by a similar technique. So if I want to solve this equation, what do? Well, I use the other property of inverses. So earlier, here, we plugged both sides into ln because I wanted ln next to e so that they antimatter annihilate. Well, I want to do the same thing here, but I already have the ln, so what I must do is plug it into e to the x. So I'm going to take this left side, I'm going to plug it into e to the x, and I'll get this thing on the left, and I'll do the same thing to the right, because again I have to do the same thing to both sides, and I get this expression. But now that e and ln are next to each other, they're essentially touching, they annihilate like antimatter, and I'm left with just the exponent, the thing inside the logarithm. And then I can solve this as usual. So pretty straightforward, I think. So that's it for this section. This section is just sort of a reminder of how exponentials and logs work. And in the most basic, the graph of e to the x looks like this. So it blows up very fast, and the graph of ln x looks like this. And hopefully you know that a function and its inverse have the property that they are reflections about this green line y equals x. So you can see there's a symmetry here, where this function is going down to 0 to the left and going up to infinity to the right, and this function is getting closer to the x value 0 as it gets closer to the y value 0. It's getting closer to the x values minus infinity, or 0, as the y value goes to minus infinity. And as it goes to the right, it goes larger. So these are the basic pictures of these two functions, and we'll draw them many times. So I'm not super concerned with understanding how they look at this moment, but it's nice to see them at the end. So we will deal with these a lot.